My name is Jens Paulsson and I will present the electric power library. Let's start. I've been with Modelon since 2010. I'm a mechanical engineer, and this is not my library, so you have to excuse me if I cannot go into detail about everything.
Connexion à la conférence.
So the agenda will be following. What is APL and what are the key features and applications? I will give a couple of examples where you could use this library and also present some of the contents. Finally, I will have some articles based on some references for this library. So let's continue to the first slide. So basically, EPL is a library for Modelica library for all kinds of simulation analysis of electric power systems, all the way from generation to transmission and distribution of electric power. It's quite flexible, and you could use it for also
Teilnahme am Meeting.
Commissioning, for testing new control strategies, for development and verification of new designs, for controller tuning, and for overall analysis of dynamics. It has been developed mainly by Hans-Jörg Wiesmann of Switzerland, a former employee of ABB Research Center, and it's now in the care of Modelon AB, and the EPL was also released last year. Formerly it was known as the Spot Library. So, to the key features of EPL, it has both transient and steady state capabilities, and it's equation based, and it has the physical representation, and this means it has a good high performance simulation capacity and accurate representation. There are a number of examples in this library for which speeds up your product development, and also to basically for increased productivity development. For the three-phase systems, we have different frame representations, the ABC and the DQ and DQ0, and EPL is basically real-time capable, and you can also increase the simulation speed by for the linearized AC systems. And the library basically it's divided between components for DC systems, for AC one-phase systems, and AC three-phase system. And again, for three-phase system we have different representations, ABC and DQ0. And you could also work directly on power flow approximations. So key capabilities, it's basically what applications we can use APL, and there's a wide range of applications in industries connected to electric power generation and grid connections. We also can use it for transmission systems and also for autonomous electrical systems on board aircraft, ships, trains, vehicles, etc. Recently we have done substantial work on wind power and renewable energies, containing also power electronics such as converters, inverters. It can be used for islanding power generation, disconnected from the grid, so to say. We have also electrical motors, AC and electrical motors with different frequency, and this EPL is compatible with the hydropower plant and the thermal power plant, which allows a complete power plant and electrical simulations. The compatibility lies in the connectors, basically.
Joining the meeting.
Now we can see some of the use cases. First of all, I will present the wind power control and calibration, and after that the turbo generator and the line. A wind park has been basically modeled and simulated all the way from wind energy to the electrical generation by the generator, the conversion to DC link, and the inverter to take it back to AC with the grid compliancy. So this work was also including controllers, a number of local and overall controllers, for example to control the power and for the tip speed ratio of the rotor. Another work, well, we could
Joining the meeting.
We can continue to the next slide, which shows the representation in Dymola of the same
En cours de connexion à la conférence.
of the very same system. Yes, again the controllers, the rotor model, which in turn is consisting of submodels, which is not shown here. The generator, again the inverter, the DC link, the inverter to grid compliant electricity, and yes, more or less this. Let's go continue.
Teilnahme am Meeting.
So
Auswahl.
we have also done a calibration of different parts of this wind power system. Basically the three components consisting of the rotor, the converter, and the generator. And we will also run this example in island control mode. We have seen that it complies with the grid code, and also use this DC link as mentioned before. So let's continue. This work was done together with the Lund University Division of Industrial Electronics and Automation. The next slide shows a turbo generator and a line, which is modeled and simulated in EPL with standard components. Basically a turbo group, a generator and a line, and some kind of grid connection. There is also a system reference block, so to say, where you set the overall features such as frequency of the system. Okay, this is another example, so I will continue to next slide. This shows the library contents, the main packages of electric power lib. It consists, as mentioned before, of packages of DC components, of AC one-phase components, of AC three-phase components in ABC representation, in three different representations: the ABC, the DQ0, and the DQ. And the DQ representations are transformed reference frames to allow for increased simulation speed, and the DQ is a symmetrical variant of the DQ0 reference. We have a number of auxiliary blocks, so to say. We have a blocks package, special signals, partial models, and so on. I will also show this when I open the EPL. We could make a small look at that later on. Another package is called common, where some common components are packaged together, which are used in all systems. We have a mechanical package basically masses and so, and we have the semiconductors for power electronics, and some interfaces and so on in the basic package. In the interface, of course, we have the stream connectors and interfaces in all domains: electrical, mechanical, and thermal. And in the parameters, there are some predefined parameters for certain devices. So let's look at that later on. Okay. I'm nearly finished with this presentation. As mentioned, we have a reference on this work, on the work with the wind power simulation. It was presented at the Modelica conference last year in Germany, and the link you could see here to this article. The main author, Hans-Jörg Wisman, has also written an article on a Modelica conference some years ago on this topic, advanced modeling of electromagnetic transients in power systems, which is the work which was behind the EPL, so to say. Okay, let's switch to Dymola and the EPL.
Connessione alla riunione.
Is there any questions so far before we start looking at the Dymola and EPL? Okay. This is electric power library as it looks in Dymola, and as normal Modelica library, we have the user guide on top. We have a number of examples as mentioned before, some introductory examples and examples for each of the main components, the DC and the AC systems components. And yeah, some data, predefined data, are contained in this block data. So let's go into, for example, this AC three-phase ABC representation. We have a different, again, for inverters, drives, generators, and so on. And in the generators package, we have the turbine generator line, which was presented in the PowerPoint just recently. Again, this is how it looks in Dymola, and let me see. We could just run the example. Could just run the example. I'm not going into details about this example. I'm just showing, yes, any output actually. On the generator side, we have a number of variables and parameters we could plot, and we could, for example, the voltage for each of the phases.
Teilnahme am Meeting.
Robert Klein.
And of course it's a high frequency, so you could also go into detail and see how it looks. You could look at the currents in the same way. For the DQ example, it would be straight lines actually for the current and voltage, because it's transformed. But ABC contains the actual sinus waves of the electrical current and voltage. yes, you know a Modelica library and how it's basically structured in these packages, and that you could also search for certain variables. For example, something contained V or voltage, you could see. Yeah, I'm not going to show you much more, but I would recommend you to maybe to start up an example yourself and to run it and to plot different variables. Yes, I can go back to the actual library and let's go down. This was the examples, right? Let's go down to the different sub-packages, the DC components. The DC components package contains a number of sub-packages, as you can see here, ranging from breakers to drives. The drives, for example, DC drives, has this layout, and let's go to the next, the AC one phase. It's also consists basically of the same structure, but yeah, also has transformers and again breakers, loads, and so on. The AC three-phase ABC representation is pretty much the same structure, but in another representation. The DQ0, the same again, and the DQ. The DQ was again the symmetrical variation of the DQ0. So you could see it's basically the same structure in each sub-package, which simplifies things for the user. Okay. In the blocks was some auxiliary components. We have some special signals, we have some partial models, and some math functions. If you're interested exactly how these blocks are connected to the main components, I will have to go back, get back. Some common components used by all electrical systems are divided between electrical, thermal, switching types. Yeah, this is just example what the electrical subcomponents look like in this common block. Okay. We also have this controls block consisting of exciters, governors, relays, and so on. It's yeah, exciters are used for the generators, of course, and all right, the mechanics package consists of basically rotation and translation models, including torque and yeah, and gears and so on. Okay. We also have the semiconductors. It's ideal semiconductors and phase modules. And finally there is this basic block, which are just again some basic components, auxiliary components. Well, and the parameters blocks contain certain parameterizations of certain devices, such as DC systems, AC, and so on, transformers, and so on. Yeah, the user guide is contains our structure where we try to give the new users information about different aspects of using the library, how the structure is made, and what units, SI units, or a relative unit called PU. The different representations I mentioned, which are clearly stated here, the one-phase and the three-phase representations. Yeah, so this is the information layer here. Some information about simulation, initialization, and so on. There is also the release notes. Basically, we have this version 2.0 released last year, as I mentioned, and there are a few words about the updates from previous. The previous library was called Spot. It's not called so anymore. It's called APL. Okay, and contact information as we usually have it. So, is there any questions so far? I can try to answer it, or if you want me to.
Yes, please.
Yes.
I have a question. I'd like to understand what are the typical scenarios to use this library on the automotive market.
On the automotive market, that would be in electrical hybrid cars, I would say, where you have the battery and electric systems involved.
So it would be typically for the dimensioning of the key components of the hybrid system, like the motors, battery.
Yes, Dymola and the transient simulation tools are maybe not always used for dimensioning purposes, but more on operational behavior, for dynamic analysis, for controls tunings, and such things. But there are certain design aspects also involved, of course. I don't think we have an automotive example, though. That would be quite good to have. We also have this other library called Battery Library, which also could be used for these hybrid vehicles. But I can't, on top of my head, I cannot see if we have any automotive example actually.
Thank you.
Yes.
Second question, what is the use of the ECU models I saw in the demo?
In the demo?
Yes, I saw that you had a part of the library which was related to ECUs, or to...
in the example I showed, is that what you... was it in this example?
It was on the left part where when you were navigating on the different categories of models, and you had the semiconductors.
Oh, okay. The semiconductors. That's a package of models. You want to know what
is it used for in that context?
This question I have to get back to you on. This is probably used for power electronics if you want to in detail model converters and inverters. This is we could go here, and it doesn't say on this info layer. Yes,
Okay.
So I would have to go back, but semiconductors is it's my belief it's used in power electronics, which can be modeled with this library also.
Thanks.
Yes.